So first of all, we have TinyMLPerf development of a benchmark suite for TinyML systems. This will be presented by Csaba, Internet of Things engineer at Digital Catapult UK.
Thank you. Thanks for the introduction. So this is a talk about the development of the MLPerf Tiny benchmark, which has just been released. And the slides, the presentation was prepared together with Corby Vanbury from Harvard University. And actually, the content behind is coming from a huge community, which I will have a dedicated slide to that. So let me introduce that later. So about benchmarking and the development of benchmarks. First of all, why are we benchmarking? And benchmarking is something which is benchmarking helps you to measure the progress of a field. And here we are obviously speaking of TinyML. And maybe even more importantly, benchmarking, if done well, and I hope we did a good job, even if it's just the first release, it is something that on the long term can raise the bar. It can advance the field. It's something which creates competition, which helps showcasing things. So overall, for the community. Now, benchmarking also requires some rigor in defining a fair and rigorous methodology, and needs community support behind it. And if done, it provides many things. It standardizes the use cases, which are interesting for the field. It provides comparability by having verifiable and reproducible results. And it just provides a complex characterization of systems. Now, about TinyML benchmarking, I think everyone would agree here that TinyML is somewhere in the crossroads of machine learning and embedded systems. And there are machine learning benchmarks out there. There are embedded systems benchmarks out there. There are even organizations specialized on these benchmarks, like ML Commons for measuring, for the MLPerf series, measuring ML inference and training performance, or Embassy, which is very well known in the embedded space. But in the section of these two, there were basically nothing. So that's how MLPerf Tiny was born now more than a year ago as an initiative. And then later it was basically ML Commons and Embassy joined efforts, and now it's encompassing the ideas of the two organizations and all the people behind them. So I will speak about this benchmarking and the development, and I will speak about this through the design challenges, and basically categorizing in three categories. The first one being how we select the use cases, which one should we focus on. The second is really in a systems design challenge or systems benchmark design challenge, which is TinyML. In TinyML, we see very fast innovation in many things, from hardware, software, model tools, and so on and so forth. So how we design a benchmark which kind of supports this variety. And the third one is what we measure, actually, what we expose, what are the right metrics, and how we measure them. So starting from the first one, the use cases. And let me just not go through the use cases. I think in these days we will see lots of presentations on many use cases. The process definitely started with a mapping of use cases, and the important thing I would highlight behind this is the community behind the mapping, and then behind the selection of the ones which form the first set. So pulling the strings, there are the group leads, Vijay and Corby from Harvard, and then one should prepare also benchmark harness and benchmark tools, and Peter Turelli from Embassy and Nat Jeffries from Google did that. And then there was the working group meetings actually once per week. So lots of contributions from many companies. And at one point, there were benchmark owners who were responsible for developing benchmark to some extent, from which I will speak later. Jeremy from Sintient, Nat, Pietro, and me. So which are the benchmarks that we have selected? We have selected 4 of them. And from left to right, I think I don't have to introduce the first one, which is really in the foundations of TinyML, the keyword spotting example. The second one, Visual Wakes, is a very nice example of using MobileNet in tiny devices. On the third one, there were actually lots of debates. Anomaly detection is an interesting field, and you can do it based on different sensory inputs, based on different data. At the end, we choose the anomaly detection, and we choose the audio-based anomaly detection, and we choose it based on having an underlying very nice competition, the D-case competition, which provided us with lots of results in this direction. And finally, image classification, which was the last one, which was added, and I think cannot be missed from this group of benchmarks. Now, as you can see, the models are quite diverse, and that's intentional. So the underlying models are quite diverse. The number of parameters are quite diverse. The datasets are quite diverse, and that's just to try to capture the high diversity of this field. Moving on, let's see how do we try to capture actually the complexities of TinyML systems, which was quite challenging. So the question here, I think, where we should start is how we define a benchmark for such TinyML systems. And there could be different approaches. One could be we define an evaluation dataset, and the device under test would run through that evaluation data test, and we would measure, and we would have benchmark metrics. Now, this could be very vague. We could have rules around it, but that's not the approach. Another one is, which is used in benchmarks, is to have portable code, which you put on device under test, and it's an evaluation data set. It's done through that you measure, but that's again not something which is fitting embedded systems. We have a huge variety of systems, of hardware around, of frameworks that should run this. So we were going for something different, and these are the two which we were going for. So on the right one, there is what I was calling the reference model. So here, the reference model is provided with its weights, and an evaluation data set is provided, and that allows us to run. It allows some submitters to code it, and then it allows benchmarks to be run and measured. Then there is and that's actually nice, but the model is then fixed. So it allows comparison, but it doesn't allow really to showcase many things which would actually mean progress in some of the fields. So there is another variant where the training data set is provided, but the model is not, and the model can be retrained, changed, and so on and so forth. And then there are the nuances. So for example, for the reference model, do we provide it in floating point or in already quantized? And the choice was to provide it floating point 32, and the quantization is something which the submitters for benchmark can change and play with. Also, because of the differences in hardware, some might not want to go in 8, but go down to in 4, etc., etc. So different bit levels, different hardwares have different capabilities there that one might want to showcase. So the reference model version we call the closed division, and the other one is the open division. But code is still something which is interesting. It's not because we provide code which has to be run on the system, but we do have something which is called reference implementations. Now, reference implementations are important for many reasons. First of all, it means open source code. So it's an implementation of the benchmark itself. It means open source code, which is basically accompanying the rules of the benchmark and the definition of the benchmark. So it's something which is very useful for those who are submitting them to this benchmark. And it's actually not just code; it's a whole modular and open process which has its own components, and then submitters can pick from that, reuse it, or change parts. So it helps submissions through its structure. And finally, a reference implementation is also running on a reference platform. it's not generic enough to run on anything. It's running on a reference platform, and on that reference platforms, it provides reference metrics. Reference metrics are not something which are super optimized. But it is a reference for everyone else. So when we are speaking of reference platform, we have actually decided to use the same reference platform for all 4 benchmarks. And this is an ST-L4, which we use the nuclear board based on this L4 version. And it's we've chosen it for many reasons. One is it's an open platform. It is widely known, available and affordable. Anyone can get it easily. It's an ARM context M4. It has enough flash and enough RAM to encompass everything we need. Then it's running ARM embed, which is again means open source, and it means portability to some extent. And it's very nicely supported by the TensorFlow framework. So the full toolchain can be utilized. Finally, what we measure. So what we measure in such a benchmark is are the metrics of interest for us. And it's relatively clear what we should measure, but there are the details, obviously. So latency is a prime metric, and it can be millisecond per inference, so time per inference, or maybe millisecond per task, because the actual execution of the task is not always just the inference. Accuracy, there are different metrics, and we should decide and standardize somehow. And then measuring energy has its own complexities. For example, what should be included in that energy measurement? And also, for example, in the latency measurement. Do the loading of the data before running the inference is included? Does preprocessing included? So here I was also listing some difficulties that we solved one way or another in this version. So whether we include pre and post processing in the benchmark, what we do if it's not just a single inference, but we have some more complex problem, how we measure power accurately, how we do timestamping, and in general, what happens with data ingestion, which in the tiny space is definitely a challenge. Not all devices that we want to measure has USB or serial connection, for example. Sometimes we have to queue the data through something else. They might not have the space to load the data, etc., etc. So for all this, we are using the Embassy benchmark runner, which you see here on the right. This is a screenshot. It is nicely running on every host platform, Linux, Mac, Windows, and it can be used to rerun the benchmark. Now a little bit more about the metrics, because each one, as I said, each one has its little specialties. So starting with latency, we decided to exclude the loading of the data, and then the evaluation is done in basically in a loop of inference. So data is loaded once, and then there are some warm-up runs, and then a number of measured runs, because inferences can be quite fast. So if we want accurate results, we do want to have a number of runs and then average. Interesting things came up. For example, data-dependent execution paths might be in some hardware software solutions. So at the moment, that's ruled out, but that's something in the next release we should think about. Then for measuring accuracy, we are using obviously larger data set to do that. Everything is done once, and accuracy is measured, and we are going for top 1 accuracy and area under curve. Here, the interesting thing is that in the closed one, so where we have the provide, where we have the model with the weights, its role is to verify that the implementation is actually doing what it is supposed to do. So it has to meet a threshold around what the reference implementation provided. In the open one, we do not have an accuracy requirement, so that it becomes part of the 3 metrics and exploring the design space. Finally, for energy, the rules say, and there are many rules, I just highlighted one, which is no cherry picking of the actual device under test from the batch. It has to be something which, if I would buy one and reproduce, and by the way, all this is reproducible by anyone easily, it would give the same results. And then we have a power monitoring setup, again, thanks to Embassy, which is again based on an ST power monitoring board, which the whole setup is less than $100. So it's easily reproducible anywhere. And then we are going for the $1 million result. Now, putting all this together, I've went through different steps from, and we as a work group went through different steps of problem definition, data set selection, model selection training, designing a tiny version of that model, quantization, writing a C implementation, integrating with the benchmark harness of that code, then deploying on the device, running a benchmark, and once there are submissions, reviewing and auditing those submissions. Here I'm summarizing who should do what, and definitely there's the work group, there are the submitters, but submitters are also in the work group, fortunately, and we have these two types of submissions. Here I'm showing on the last slide, I suppose I don't have too much time, an example for the anomaly detection, just walking through the process. Anomaly sound detection, we used, as I said, the DK's 2020 competition as our baseline, both as data set and as the way the model was derived. It is something which is actually, it was a special case in the sense that the audio, which is around 10 seconds, is transformed into spectrogram, but then inference is on a sliding window multiple times, and it uses an autoencoder. So the autoencoder is encoding each window once, and then this is over the whole spectrogram. This gives an anomaly score, which is the smaller, the better, the larger anomaly is detected. This means that to have accurate results, we have to run it on the whole spectrogram, while for measuring latency, we decided to, and consumption, we decided to focus on the individual inference. So that was one of the challenge. We do have the code. Yep.
Awesome presentation. I'm going to have to put a break because we're running out of time. I'm going to ask everyone that's listening, if there is any more questions for Csaba, you can post them in the chat or in the Q&A section, and Csaba will take them afterwards. So thank you so much.
I would like to acknowledge again our sponsors. The sponsors are the ones that actually made having a free registration for everybody possible, starting by Newton.ai, who is innovating into the automated TinyML domain, who's also our premier sponsor. Next, we have the executive sponsors. We have ARM, which, as you know, builds from both the software and the hardware foundations for TinyML. We have Edge Impulse, who is advocating strongly, as you all know, for TinyML available to all of the developers. And of course, Qualcomm, who is working as, among other perception, reasoning, and action, and edge and cloud devices in various sectors, such as the Internet of Things, automotive, and mobile applications. And Sentient, who is moving artificial intelligence from the cloud to the edge, which, as you have seen today, it's quite now the trend nowadays. Next, we have our platinum sponsors, Infineon, part of your life, part of tomorrow. We have seen a few of their projects that they work today. We have Reality AI, who is working also in pre-built edge AI sensing modules and tools. Next, we have our gold sponsors. Latent AI is the first one who works on adaptive AI for the intelligent edge. Then we have SenseML, which works on building smart IoT sensor devices from various data. And last but not least, our silver sponsors, EMEA from Israel, Greenwaves, HOTC, Magimop, Quixo, Seed, Studio, and of course, ST Microelectronics. I would like to thank everybody that stuck around until now, and I hope to see everybody tomorrow at 4 o'clock Central European time